That one? Okay. We're good.
Good afternoon, my name is Michael Sherritt. I'll be presenting on behalf of the Green Team, which consists of Mark Bree, Matt Baltimore, and Michael Newman. And I'll be talking about the aerator mixing station today. Here's an overview of what I plan to talk about. I'm not sure what I'll be able to talk about today. I'll be focusing on the sign and relay, the blue logos, and proportional controller experiment. Here's This is our amazingly interesting steady-state operating mode. Linear from 0 to 100% is corresponds to an output of 0 to 1,740. These are our error bars. These are our input points. The little red boxes are actually our error bars. Here's the block diagram for our sign response. This is the transfer function right here, and our input and output are both sign-based. Here's an example at half a hertz. The amplitude ratio is found by taking the amplitude of the output and dividing it by the input. And our phase angle tells us how much the output is like the input. For this particular experiment, it was about 38 degrees. Here's a Bode plot for my region, which is the 75 to 100% region. What we've done here is for the phase angle, we see where it's equal to 180 degrees, and we go up to the amplitude ratio, and we're able to find the ultimate controller gain and the ultimate frequency, which for this experiment were 0.37% RPM and 3.4 hertz. These were in the, we're also able to get K, the time constant, and dead time. K was the asymptotic value of this region right here, which is about 17.1. Then tau was about 0.15 seconds, and T naught was about 0.17 seconds. And then taking the slope of this region right here and taking the negative of it will give us the order which we set out to. Here's both Bode plots that we did for mine and Michael's results from the sign, and these are compared with the model results. The model are the lines, and the experimental are the data points. What we've done here is we had a perfect model to compare our data to, and then we adjusted the model to match the data as closely as possible to tell us what the FOPT parameters were. For the 75-100% range, it was 17.1 RPM per percent. Dead time 0.8 seconds, and tau 0.17. For 50 to 75, it was a gain of 17.3, a dead time of 0.09 seconds, and a tau of 0.16 seconds. Here's a comparison of the gain between the experimental and the model, and then matched up very close. The dead time was a little bit different. The experimental was consistently higher. Time constant, however, matched up pretty close between experimental and the model. Here's a relay response example. It consists of a set point, and the input was a sine wave for this experiment, which had a floor and a ceiling. Once it crossed the set point, or once the output crossed the set point, it would change and try to adjust it and keep it focused around the center of the set point.
Can I ask you to pause just a minute?
Certainly.
Back then, Aaron, wouldn't you love to see something like that?
Oh, yes.
Huh? Too bad.
I was not responsible for that in any way. Don't hate me.
I don't hate you. You're just lucky.
This is a comparison of the gain in between the frequency and the relay response. They were close to each other within the experiment and within the experiment here, but not so much to each other. tau, they were definitely not the same, but overall we think the signed soil experiments turned out a little bit better than the relay response. Here they were fairly close in these regions, but not on the others. Overall, the frequency experiment more closely agrees with what was found for K, T naught, and tau than those from the relay experiment. Here's our transfer function for the FOPDT system, and once you substitute today's approximation, it becomes this right here. For a proportional feedback controller, the transfer function is given by this equation right here, and then our open transfer function for a proportional control in FOPD is this. And from this, we can get a characteristic equation, which is 1 plus OLTF. Solving this characteristic equation will give us roots that allow us to make a Bode plot, such as this. This is for the 50 to 75% range. Going from the ultimate to the critical, they range from 0.26 down to about 0.017% RPM. Here's a comparison between the root locus relay and the frequency experiments. They were pretty consistent at about 0.3, except for this one right here, which was Matt's region. We don't really know what happened there. It was a relay experiment. But once again, we think the frequency experiments turned out better than the relays. For the ultimate frequency, there just really wasn't a comparison. The root locus was consistently higher than all the other ones. This is a Bode plot using the parameters we thought were best for our system. Those were taken from the, root locus, did I say Bode? The parameters were taken from the Bode plot, which gave us the best numbers for our system. So for critical damping, it was about 0.018, 1/500 was 0.061, 1/10 was 0.14, and then the quarter damping was 0.18, and the ultimate was 0.2. Here's a control gain experiment for the ultimate gain. Offset is in between the set point and the average of this, and it just continues to oscillate and doesn't die down. The set point was at 1,650 RPM, and then my M bar was 95%. And then it took a step down of 250 since it was in the upper region. So the offset was 34 RPM, had an overshoot of 6%, and didn't have 7 times since it never really settled. And then the gain is 0.3% per RPM. Here's the same thing except for quarter decay. Offset got a little bigger, overshoot went down, and settling time was about 1.2 seconds. Same thing again for 1/10. The offset got bigger, and the overshoot got a little bit smaller, and the settling time went down. For 1/500, same story. The offset got bigger, overshoot went down, and the settling time went down. Critical, we still see the same trend. Overshoot went down to 0, settling time went down. But the offset got a lot bigger. So this is a comparison of what we got from the root locus, what it was telling us it should have been. This is what we actually got. They were fairly close, but this is how our system actually behaves instead of what was predicted to behave. Settling time went down, and then the offset went up, and the overshoot went down. So it really depends on what the customer needs to make our recommendation. In conclusion, the SSOC shows a linear correlation between input power and speed, and has an operating range of 0 to 100% and 0 to 1,740 RPM. The gain of the system is equal to the slope of the SSOC, and the experimental model result match fairly closely. It's a second order system, and then these were taken from the Bode plot. These are considered the best FOPDT parameters for our system. The KCU from Blue Locus agreed with what we found from the previous experiments, but the ultimate frequency did not. So based on the experimental results, our gain ranges from 0.02% RPM to 0.29% RPM. And knowing how our system actually operates, we can make recommendations to the customers. It's not a one-size-fits-all with between quarter, tenth, and 500. So based on what they want, whether they value a lower offset or a faster response time, we can make recommendations based on what they want. So, and that concludes my presentation for the mixing station. Questions?